Subscribe to Dr. Khalkar's classroom channel and press the bell icon to get latest updates. Hello everyone, I hope you are doing great. In my previous lecture video, I have discussed about p-n junction and diode equation. In this lecture video, I will discuss about application of p-n junction with example of solar cell. So let's get started. The content of this lecture video is as follows. First of all, I will discuss upon photoelectric effect and photovoltaic effect. Followed by, I will discuss upon basics of solar cells, types of solar cells and efficiency chart, air mass, solar spectrum, PV system, and advantages, limitations, and applications of solar cells. So let's see photoelectric effect. The photoelectric phenomena I have already discussed in unit number 3, that is wave mechanics. However, let's have a brief introduction about it. The photoelectric effect is a phenomena in which electrons are ejected from the surface of a metal when light is incident on it. These ejected electrons are called photoelectrons. It is important to note that the emission of photoelectrons and the kinetic energy of the ejected photoelectrons is dependent on the frequency of the light that is incident on the metal's surface. The process through which photoelectrons are ejected from the surface of the metal due to the action of light is commonly referred as photoemission. The photoelectric effect occurs because the electrons at the surface of the metal tend to absorb energy from the incident light and use it to overcome the attractive forces that bind them to the metallic nuclei. An illustration detailing the emission of photoelectrons as a result of the photoelectric effect is shown in this animated diagram. Now let's see what is photovoltaic effect. The photovoltaic effect is the generation of voltage and electric current in a material upon exposure of light. It is a physical and chemical phenomena. In either case, light is absorbed, causing excitation of an electron or other charge carriers to a higher energy state. The main distinction is that the term photoelectric effect is now usually used when the electron is ejected out of the material, usually into a vacuum, and the photovoltaic effect used when the excited charge carrier is still contained within the material. In either case, an electric potential or the voltage is produced by the separation of charges, and the light has to have a sufficient energy to overcome the potential barrier for excitation. This physical essence of the difference is usually that photoelectric emission separates the charges by ballistic conduction and photovoltaic emission separates them by diffusion. But some hot carriers photovoltaic device concepts blur this distinction. Now let's see the photovoltaic effect in solar cell. The collection of light generated carriers does not by itself give rise to power generation. In order to generate power, a voltage must be generated as well as a current. Voltage is generated in solar cell by a process known as photovoltaic effect. The collection of light generated carriers by the p-n junction causes a movement of electrons to the n-type side and holes to the p-type side of the junction. Under short circuit conditions, there is no build-up of charge as the carriers exits the device as light generated current. The short circuit and the potential voltage and barriers, everything related to the solar cell I will discuss in detail later. The electrons of the semiconductor material are joined together by the covalent bond. The electromagnetic radiations are made of small energy particles called photons. When the photons are incident on the semiconductor material, then the electrons become energized and starts emitting. The energized electron is known as the photoelectrons, and the phenomena of emission of electrons is known as photoelectric effect. The working of the photovoltaic cell depends on the photoelectric effect. The photovoltaic effect is closely related to the photoelectric effect. So this is the difference between photoelectric effect and the photovoltaic effect. Now let's see solar cell in detail. A solar cell is an electronic device which directly converts sunlight into electricity. Light shining on the solar cell produces both a current and voltage to generate electric power. This process requires firstly a material in which the absorption of light raises an electron to a higher energy state, and secondly the movement of this higher energy electron from the solar cell into an external circuit. The electron then dissipates its energy in the external circuit and returns to the solar cell. A variety of materials and processes can potentially satisfy the requirements of photovoltaic energy conversion, but in practice nearly all photovoltaic energy conversion uses semiconductor materials in the form of a p-n junction. So basically solar cell is nothing but a p-n junction diode. The basic steps in the operation of solar cell are the generation of light generated carriers, the collection of the light generated carriers to generate a current, the generation of a large voltage across the solar cell, and the dissipation of power in the load and in parasitic resistances. So these basic steps are very important in the mechanism of solar cell. Now here let's see the construction of solar cell. A thin layer of p-type semiconductor material is doped over a n-type substrate forming a p-n junction. The thickness of the p layer is very small. The electrical contacts are made over the top and the bottom sides. To enhance the transmission of light into the material, an anti-reflection coating is given over the p-type layer. Now let's see the working mechanism of solar cell. First of all, light generated current. The generation of current in a solar cell, known as the light generated current, involves two key processes. The first process is the absorption of incident photons to create electron-hole pairs. The electron-hole pairs will be generated in the solar cell provided that the incident photon has an energy greater than that of the band gap. However, electrons in p-type material and holes in n-type material are metastable and will only exist on average for a length of time equal to the minority carrier lifetime before they recombine. If the carrier recombines, then the light generated electron-hole pair is lost and no current or power can be generated. A second process, the collection of these carriers by the p-n junction, prevents this recombination by using a p-n junction to spatially separate the electron and the holes. The carriers are separated by the action of the electric field existing at the p-n junction. If the light generated minority carrier reaches to the p-n junction, it is swept across the junction by the electric field at the junction, where it is now a majority carriers. If the emitter and the base of the solar cell are connected together, that is, if the solar cell is short-circuited, the light generated carriers flow through the external circuit. The ideal flow at short circuit is shown in this animated figure. In the working of solar cell, when the sunlight falls on the upper P region, it generates the electron-hole pairs in both p and n regions. Thickness of p layer is very small. Hence, the probability of recombination of electrons and holes is less and they immediately reach the p-n junction. At the junction, barrier potential attracts electrons from p region into n region and holes from n region into p region. This leads to an increase in the number of holes on p region and electrons in the n region. The accumulation of charges on the two sides of the junction produces a voltage or EMF known as photo EMF. It is known as the open circuit voltage and is proportional to the intensity of the incident light as well as the size of the illuminated area. If an external circuit is connected across the solar cell terminals, a current flows through the circuit. Now let's see the simulation of carrier flows in a solar cell. If the light generated carriers are prevented from leaving the solar cell, then the collection of light generated carriers causes an increase in the number of electrons on the n-type side of the p-n junction and a similar increase in the holes in the p-type material. This separation of charge creates an electric field at the junction which is in opposition to that already existing at the junction, thereby reducing the net electric field. Since the electric field represents a barrier to the flow of the forward bias diffusion current, the reduction of the electric field increases the diffusion current. A new equilibrium is reached in which a voltage exists across the p-n junction. The current from the solar cell is the difference between IL, I stands for current, L for load, and the forward bias current. Under open circuit conditions, the forward bias of the junction increases to a point where the light generated current is exactly balanced by the forward bias diffusion current and the net current is zero. The voltage required to cause these two currents to balance is called the open circuit voltage. This animation shows the carrier flows at short circuit and open circuit conditions. Now let's see the IV characteristics of a solar cell. Typical IV characteristics of solar cell can be studied with a simple circuit which is shown in this diagram. The IV curve of the solar cell is the superposition of IV curve of the solar cell diode in the dark with the light generated current. The light has the effect of shifting the IV curve down into the fourth quadrant where power can be extracted from the diode. Illuminating a cell adds to the normal dark currents in the diode so that the diode equation can be written as IL is equal to I naught in square bracket exponential of EVF divided by KT minus 1 square bracket complete. This is nothing but the diode equation where I naught is equal to J naught upon A, IL is the light generated current where V denotes the voltage if V is equal to VF is for the forward biased and V is equal to minus VR for the reverse bias. And I naught denotes the reverse saturation current. In IV characteristics of solar cell, let's see what is short circuit current, that is ISC. The short circuit current is the current through the solar cell when the voltage across the solar cell is zero. That is when the solar cell is short circuited, usually written as I subscript SC. The short circuit current is shown on the IV curve which is shown here. Short circuit current initially when the load resistance, let's say RL, is kept minimum, the maximum current flows in the circuit. When the load is zero, let's say RL tends to zero, maximum current is known as the short circuit current. The short circuit current is due to the generation and the collection of light generated carriers for an ideal solar cell at most moderate resistive loss mechanisms. The short circuit current and the light generated current are identical. Therefore, the short circuit current is the largest current which may be drawn from the solar cell. The short circuit current depends on the number of factors which are the area of the solar cell. To remove the dependence of the solar cell area, it is more common to list the short circuit current density, let's say JSC in milliampere per centimeter square, rather than the short circuit current. Next factor is the number of photons, that is the power of the incident light source. ISC from a solar cell is directly dependent on the light intensity. Next is the spectrum of the incident light. For most solar cell measurement, the spectrum is standardized to the air mass 1.5 spectrum. So what is air mass? We will discuss later. Next factor is the optical properties, that is absorption and reflection of solar cell. The collection of probability of the solar cell which depends chiefly on the surface passivation and minority carriers lifetime in the case. The IV curve of the solar cell which is showed here is showing the short circuit current. Now let's see open circuit voltage of solar cell in the IV curve. The open circuit voltage, ideally when the circuit is open, voltage is maximum and current is zero. This maximum voltage is open circuit voltage and denoted by capital V subscript OC. The open circuit voltage VOC is the maximum voltage available from the solar cell, and this occurs at zero current. The open circuit voltage corresponds to the amount of forward bias on the solar cell due to the bias of the solar cell junction with the light generated current. The open circuit voltage is shown in this IV curve. Let's see the variation of current with voltage. As load resistance is increased, the voltage across the load resistance, that is RL, increases and the current starts decreasing. When the load is maximum, that is RL tends to infinity, the current is very small and the voltage across the load is maximum. Now let's see the important parameter of the solar cell, that is the fill factor. The short circuit current and the open circuit voltage are the maximum current and voltage respectively from the solar cell. However, at both of these operating points, the power from the solar cell is zero. The fill factor, more commonly known as the abbreviation FF, is a parameter which is conjunction with VOC and ISC, which determines the maximum power from a solar cell. The fill factor is defined as the ratio of the maximum power from the solar cell to the product of open circuit voltage and short circuit current, so that maximum useful power obtained experimentally, that is Pmax, is equal to Imax into Vmax, where Pmax is the maximum power, Imax is the maximum current, and Vmax is the maximum voltage. Ideal power output from the solar cell, let's say P ideal, is equal to ISC into VOC, where Imax and Vmax are the maximum values of current and voltage obtained experimentally. Therefore, we can write fill factor is equal to maximum useful power divided by ideal power. So therefore, fill factor is equal to Imax into Vmax divided by ISC into VOC. The maximum useful power obtained experimentally is always less than the ideal maximum power. The value of fill factor is less than 1. Usually the value of fill factor is around 60 to 70%. Now let's see next important parameter of the solar cell is efficiency of solar cell. Efficiency of solar cell is defined as the ratio of energy output from the solar cell to the input energy from the sun. The efficiency is the most commonly used parameter to compare the performance of one solar cell to the another. In addition to reflecting the performance of the solar cell itself, the efficiency depends on the spectrum and the intensity of the incident sunlight and the temperature of the solar cell. Therefore, the conditions under which efficiency is measured must be carefully controlled in order to compare the performance of one device to the another. Terrestrial solar cells are measured under air mass 1.5 conditions at a temperature of 25 degrees Celsius. Solar cells intended for space use are measured under air mass 0 conditions. So what is air mass 1.5 and air mass 0 we will discuss later on. So therefore efficiency is represented by eta is equal to Im into Vm divided by incident power. So this equation also we can write eta is equal to fill factor into ISC into VOC. Usually the voltage developed by solar cell is one of the order of 0.6 volt and the efficiency of conversion is about 15 to 21% for silicon solar cells. Now let's see the types of solar cells. Depending upon the junctions and the material of the solar cells, there are several types of solar cells and that are characterized in this way. First of all, let's see multi-junction cells. In multi-junction solar cells, there are two terminals monolithic or 3-junction, 2-junction or 4 junctions are there. Similarly, there is a single junction, for example, gallium arsenide, in which a single crystal or concentrated or thin film crystals are there. Next type is crystalline silicon solar cells, in which single crystal concentrated single crystal non-concentrated, multicrystalline, silicon heterostructures and thin film crystals are there. Next type of solar cell is a thin film solar cells. In thin film technologies, CIGS concentrated, CIGS, CDTE and amorphous silicon H stabilized, these are the types, where CIGS stands for copper, indium, gallium and selenium. Now in solar cell there is another one area where the emerging photovoltaic technology has been done and they are still developing. These areas are dye-sensitized solar cells, perovskite solar cells, perovskite silicon tandem monolithic solar cells, organic solar cells, organic tandem cells, inorganic cells and quantum dot cells. So there are the several types of solar cells depending on the manufacturing or synthesis processes and the types of materials. These types of solar cells has been divided. This graph shows the best research cell efficiencies which were developed since 1975 to till date. So all several types of solar cells and their performances in terms of efficiency has been shown in this diagram. This graph shows different research groups from different universities and institutes or the industries which shows the records of the solar cell efficiencies. For the more detail, you can visit the website of nrel.gov. Now let's see the solar energy spectrum. The standard solar spectra is shown in this diagram. The solar spectrum changes throughout the day and with the location on the earth. Standard reference spectra are defined to allow the performance comparison of photovoltaic devices from different manufacturers and research laboratories. The standard spectra were refined in the early 2000s to increase the resolution and to coordinate the standards internationally. The previous solar spectrum ASTM G159 was withdrawn from the use in 2005. In most cases, the difference between the spectrum has little effect on the device performance and the newer spectra are easier to use. ASTM E490 is the standard spectrum for space applications, is referred to as air mass 0. It has an integrated power of 1366.1 watt per meter square. ASTM G17303 is the international standard ISO 9845-1 in 1992. Two standards are defined for terrestrial use. The Air Mass 1.5, that is global spectrum, is designed for flat plate modules and has an integrated power of 100 watt per meter square. The Air Mass 1.5 direct spectrum is defined for the solar concentrated work. It includes the direct beam from the sun plus the circumsolar component in a disk 2.5 degrees around the sun. The direct plus circumsolar spectrum has an integrated power density of 900 watt per meter square. The SMARTS, that is simple module of the atmospheric radiative transfer of sunshine program, is used to generate the standard spectra and can also be used to generate other spectra as required. So these are the standard solar spectra which are used to compare the performance of the different solar cell devices. Now let's see what is air mass. The air mass coefficient defines the direct optical path length through the Earth's atmosphere expressed as a ratio relative to the path length vertically upwards, that is at the zenith angle. The air mass coefficient can be used to help characterize the solar spectrum after solar radiation has traveled through the atmosphere. The air mass with different angles are shown in this diagram. Air mass dependent on the sun's elevation path through the sky. Air mass is approximately equal to 1 upon cos theta z, where z is the zenith angle in degrees. Air mass 0 is the spectrum outside the atmosphere. Air mass 1 is the sun directly overhead. Air mass 1 at z is equal to 0 degree to air mass 1.1 where z equal to 25 degrees is the location equatorial and tropical regions. air mass 1.5, where Z is equal to 42.2 degrees, where morning and evening and at the other times of the year. Air mass 2 is Z is equal to 60 degree to air mass 3 when Z is equal to 70 degree, that is average performance at high latitudes. So these are the positions of the suns and the angles which are very important to measure the air mass and the performance of the solar cell devices, which is based on this air mass. Now let's see the diagram of the possible components of the photovoltaic system. Solar cell to the PV system. PV stands for photovoltaic. Here in this diagram, from a solar cell to a PV system, it's shown initially one small solar cell which is manufactured at laboratory scale or at the industrial level, which arranged in a such a way that the solar module is fabricated. After the installation of several solar modules, a solar panel is fabricated. And furthermore, this solar panel is connected to the several PV system parameters, which are electricity meter, AC isolator, fuse box, inverters, batteries, charge controller, generation meter, DC isolator, cabling, mounting and tracking system. So this is just a overall about the possible components of the photovoltaic system, in which the solar cell is one of the important component. Now let's see the advantages of solar cell. Solar cells obtain energy from the sun and transform this into usable electricity. Renewable energy, that is the energy, can be used both to generate electricity and heat either through solar photovoltaic system or solar thermal system. Economy friendly energy. Once the installation is made, solar cell can be operated at almost no cost except maintenance. Environmentally friendly energy. Solar cell produces energy without pollution. Long-term energy. Photovoltaic systems often have a long life and a good durability. Long-term energy. Photovoltaic systems often have a long life and have a good durability. Solar cells can be installed virtually anywhere in a field to on a roof of building, etc. So these are the several advantages of solar cells. Now let's see the limitations of solar cells. First is cost. The initial cost of purchasing a solar cell is fairly high. This includes paying for solar panels, inverters, batteries, wiring, and for the installation. Nevertheless, solar technologies are constantly developing, so it is safe to assume that prices will go down in the future. Next is weather dependent. Although solar energy can still be collected during cloudy and rainy days, the efficiency of the solar system drops. Solar panels are dependent on the sunlight to effectively gather solar energy. Therefore, a few cloudy, rainy days can have a noticeable effect on the energy system. You should also take into account that solar energy cannot be collected during the night. On the other hand, if you also require your water heating solution to work at night or during winter time, thermodynamic panels are an alternative to consider. Next one is solar energy storage is expensive. Solar energy has to be used right away or it can be stored in large batteries. These batteries used off the grid solar system can be charged during the day so that the energy is used at night. This is a good solution for using solar energy all day long, but it is also quite expensive. In most cases, it is smarter to just use solar energy during the day and take energy from the grid during the night. You can only do this if your system is connected to the grid. Luckily, your energy demand is usually higher during the day, so you can meet most of it with solar energy. Next limitation is uses a lot of space. The more electricity you want to produce, the more solar panels you will need, as you want to collect as much sunlight as possible. Solar PV panels requires a lots of space and some roofs are not big enough to fit the number of solar panels that you would like to have. An alternative is to install some of the panels in your yards, but they need to have access to sunlight. If you don't have the space for all the panels that you wanted, you can have option for installing fewer to still satisfy some of your energy needs. Next limitation is it is associated with pollution. Although pollution related to solar energy system is far less as compared to other sources of energy, solar energy can be associated with the pollution. Transportation and installation of solar systems have been associated with the emission of greenhouse gases. There are also some toxic materials and hazardous products used during the manufacturing processes of solar photovoltaic systems, which can be indirectly affect the environment. Nevertheless, solar energy pollutes far less than other alternative energy sources. So these are the limitations of solar cell. Let's see the applications of solar cell. Solar cells are largely used for providing electricity to rural and remote areas where grid installation is difficult. Solar cells are used for powering telecommunication system in rural and remote areas such as transmission of signals, radio, TV sets, emergency telephone system, etc. Solar energy is used extensively to pump water from wells and rivers to villages for domestic consumption and irrigation of crops. In this space, solar energy used to power the satellites and space vehicles. Many consumer products such as watches, toys, calculators, emergency power systems uses solar cells. So these are the several applications of solar cells. Now let's see the gallery of standalone systems. First of all, mobile solar trolley. A generator to power your appliances. Take it anywhere, anytime, no installation needed, 100% solar powered. Next is a solar canopy which provides shades for vehicle parking. Next is a spacecraft that orbit Earth called satellites are close enough to the sun that they can often use solar power. These spacecraft have solar panels which convert the sun's energy into electricity that powers this spacecraft. The electricity from the solar panels charges a battery in the spacecraft. Next is a solar car. Solar car is a solar vehicle used for land transport. Solar car usually run on the only power from the sun, although some models will supplement that power using a battery or use solar panels to recharge batteries or run auxiliary system for a car that mainly uses battery power. Next is a solar impulse. Solar cells used on solar impulse, which is a Swiss long-range experimental solar-powered aircraft project. So these are the standalone systems which are shown in this gallery. Now let's see the ways to improve efficiency of solar cell. The solar cells developed using crystalline silicon technology and are used for commercial purpose have typically efficiencies ranging from 15 to 21%. There are a number of improving efficiency of solar cells. The efficiency of solar cell could be up to 45% depending on the technology used for its development. Some of the ways by which we can improve the efficiency of solar cell. First is fill factor and shape of the solar cell. Fill factor refers to the utilization of available surface area. Typically, it ranges from about 70 to 90%. Fill factor of solar panels depends on their shape. For example, round or moon-shaped solar cell have lower fill factor. Square cells have more fill factor. By choosing proper shape, efficiency of solar cell can be improved. Next is solar cells glazing. For long life, solar cells must be protected from the external factors such as rain, snow, bird dropping, etc. For glazing the solar panel, polycarbonate or low iron glass is generally used due to high optical transmissivity around 90%. Next is solar panel orientation. For highest output, solar panel must be perpendicular to the sun's rays. However, for rooftop solar panels, their orientation is fixed. For other types of fixed installations, the azimuth is oriented to the south and tilt adjusted for the winter period. Next is solar tracker. Solar tracker is the rotation of the panel so that it always directly faces the sun. However, larger the array, more difficult will be the operation. The optimum tilt angle changes slowly as the earth rotates on its axis. Next way is light concentrators. Solar panel output power may be increased to almost 50% via light concentrated such as Fresnel lens or mirrors. However, installing concentrators for a large array of solar cells and orientation of the mirror creates an additional tracking problem. Next is solar charge controls. Since the solar panel may not have the correct voltage to charge a battery, it must be controlled via solar charge controller to prevent battery overcharge. The excess power needs to be dissipated using heat sink. Next is MPPT controller. MPPT stands for maximum power point tracking. MPPT control does not turn the excess power into heat, but it turns it into additional charge current. The control senses both input voltage and current and then adjusts output to maximize power transfer. So these are the several ways to improve the efficiency of the solar cell. This is all about solar cell. In my next lecture video, I will discuss about Hall effect. So please don't miss my next lecture video. Thank you. Below this video, in the description, the link of important information related to this video is given. Please go through it. Please like and share this video and subscribe to Dr. Khalkar's Classroom channel to get the notifications about my upcoming videos. Thank you.